Can you explain about the standard argument for the block universe and then where you differ?
Yeah, the standard argument for the block universe is very simple. It's that in special relativity, you've got 4 dimensions and you've got your space-like, time-like surfaces. And when you change velocity, what seems space-like to you changes. So therefore, there are no preferred spatial sections in space-time. And therefore, we must have a block universe because there can't be any preferred spatial sections. Now, this is wrong in multiple ways. And the first point is that the big news is that special relativity doesn't describe the universe, general relativity does. Okay, so then what people say, but that makes it even worse because of general covariance. So there are no preferred surfaces of time. And the answer is, this again is the problem of physicists who think in a context-free way. Put it in this context. Every cosmological model has preferred space sections. Every cosmological has preferred time sections. That's what standard Robertson-Walker cosmologies are. They've got preferred surfaces. T is constant, preferred timelines. And so they're simply ignoring the fact that in the real universe models, there are preferred time sections. And then the further point is what they're saying is completely at odds with what the Planck team does. And there's that canonical picture of the origin of the universe, last scattering surface. And the age of the universe is stated to be 13.87 billion years. So my model of the universe is an evolving block universe. In another billion years, that right-hand edge will have moved to the right a billion years. Space-time itself will have grown. Space-time will have got bigger. And how will that have happened? Well, through the Einstein field equations. And one of the things which is confusing is that the basic field equations of physics can be written in various ways, Lagrangian way, Hamiltonian way, but they can all be written in a way which is a time-dependent way. In the case of gravity, it's what's called the ADM equations, the Arnold-Taylor-Misner equations, and those write gravity as a space-time which evolves with time. So the standard, the real view, the real situation in the universe is that space-time is evolving. It started at the beginning, which was 13.87 billion years ago. At the moment, it's 13.87 years ago. It will be another billion years older in another time. The right-hand edge will have moved to the right. Now, the further very important point is this. This establishes a global direction of time. The direction of time passes from the beginning, which doesn't move, to the present day, which does move, and the present day is moving all the time. And there's this paradox that all of the important equations of physics are time symmetric. So where do local arrows of times come from? And the answer, which I've written about, is that the local arrows of time derive from the global direction of time. And one of the strange things is that at the present time, when people talk about the arrow of time, they only talk about the thermodynamic one and the second law of thermodynamics. But actually, there's an arrow of time for electrodynamics, for gravitational waves, for sound, for thermodynamics, for all of them. And one of the striking things is they all point in the same direction of time. And they all point in the same direction of time because they all derive from the same basis. The global direction of time breaks the time symmetry. So the field equation, the physics equations are all time symmetric. Their context is not time symmetric. And so this is what I mean by a lot of physicists who think about physics in a contextless way. When you put them in the context of the expanding universe, you solve the problem. We do not live in a block universe. We evolve an evolving block universe. We get the direction of time because it derives from this expansion of the universe. And it's actually quite simple when you look at it in that way.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions Moving forward, this sort of high quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, Toe is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off. Didn't you also say that the quantum to classical transition is a problem for inflation?
Yes, that's also a problem. It's a great lacuna in standard theory, is that in that picture they show you quantum fluctuations on the left. All of a sudden they're classical, and there's almost nobody who writes about how does the quantum become classical. And until you've actually made that clear, inflation is the way that inflation is supposed to lead to fluctuation in structure is an incomplete theory. And and now I've got a theory of, I agree with Roger Penrose that wave function collapse is real. And with my colleague Barbara Drossel, I've written papers about what we call contextual wave function collapse. And that wave function collapse is real, but the way it happens is always determined by the context. And we give a very detailed example of that in our paper called Contextual Wave Function Collapse.
So it's an objective collapse theory?
Yeah, indeed. And what that means is that essentially the Copenhagen interpretation is correct. And related to this is a further thing that I've written about, is that people, and Sean Carroll in particular, they like to talk about the wave function of the universe, and that bases a lot of Sean Carroll's stuff about. He says the multiverse must happen because of well, this is obvious nonsense for the following reason. The Dirac equation and the Schrödinger equation are linear equations. Now, the real universe is not linear. So there's a paradox there. How does nonlinear stuff come out of a totally linear equation? And they try to say, well, it comes from the multiverse. Well, the real solution comes from looking back to general relativity. The great breakthrough in general relativity occurred when we discovered the concept of coordinate systems. You can't cover an ordinary space-time by a signal coordinate system. You have to have a whole atlas of coordinates, and it's the atlas which covers space-time, not a single one, and that's what enabled us to discover all the topological results in general relativity. Now, what I claim is exactly the same holds in quantum physics. There is no global wave function. That's a fantasy. There are local wave functions everywhere. And the local wave functions cover the whole space-time. But there is no single wave function for a universe, which completely undercuts the whole idea of the quantum multiverse. There's no wave function for a cat, all of that stuff. There's no wave function for a brain. And so the idea that one single wave function could encompass a whole brain is purely fantasy. It's obviously nonsense, because the key fact of quantum physics, it's quantum physics equations are linear, and the Dirac and the Feynman path integral is based in the fact it's a linear operator on the wave function. The real physics is not linear, and the way to solve that is to have local wave functions which knot together to create nonlinear structures.
You think the multiverse is nonsense? Okay, there are various kinds of multiverses. So there's an Everettian multiverse, which you referenced. There's a Tegmarkian, like a mathematical universe. That's
the one which Tegmark's one The fact that something exists as a mathematics doesn't mean it exists physically, and it's just a simple misconception. I'm prepared to believe that some chaotic cosmologies will lead to different expanding universe domains. I'm prepared to believe that. I'm not an expert in inflationary theory. But the point as a cosmologist, I'm a very conservative scientist. I believe that science is related to things which you can observe or which you can test. And in the case of the multiverse, you can't see them, you can't test them. That's because there are visual horizons. You can't see any further than a visual horizon. I can say anything I want to about it. You can say anything. Nobody can prove you're right. Nobody can prove I'm right. So I think you're talking metaphysics, not physics, when you say we're talking about those multiverses. Now, I know this is very unpopular with some of my colleagues, but I'm a very conservative scientist in that respect, because and I have to be, because when I'm talking about all of this stuff about emergence, I have to make sure I'm on sound theoretical and experimental basis. And all of this emergence stuff is completely sound. And so I'm very careful to stick what I say to stuff which can be tested or observed. Now, of course, the problem with cosmology is that there's a uniqueness of the universe, which means we can't compare it with other universes. We can't rerun the universe, do tests on different universes. And that is, in a sense, the foundational problem. We only live in one universe, and we can only view it from one space-time point on one parcel icon. That's a basic problem in cosmology.
That's also part of my problem with fine-tuning arguments or anthropic principles, where they assume that there's some prior distribution, probability distribution on some constants. And then you wonder, well, where are we selecting this from? All we have is one example.
Yeah. You can imagine anything you like. I can imagine anything I like. We can see up to the visual horizon. We can be influenced by stuff up to the particle horizon. It could be, one of the interesting possibilities is space, that the universe could close up on itself on a scale bigger than the horizon, in which case it's definitely finite. One of the ones that I wished was the truth, but it doesn't seem to be so, is that the universe closed up on itself on a scale smaller than the visual horizon. And that's what I call a small universe. And in that case, you would see the same galaxies at different directions in the sky at different times in their history. And I think, as a philosopher, I would prefer the universe to be a small universe, because in that case, our observation relation to the universe is completely different than in every other case.